Thank you very much, Claudio, for your kind words. And let's start with my first presentation, numerical validation of an energetic down-break induced flow on a bridge cross-section using the SPH method. This work is basically carried out under my supervision, humbly leading the UNISA Waves group, which is composed by Giorgia, Salvatore Capasso, Bonaventura, Professor Corrado Altomare, okay, is a colleague, and myself. Okay, with the scroll. Yeah, just a layout of the presentation. I will give some concept behind the SPH method, and some results and related conclusions. The problem, unfortunately, is of, is, of is actual, I will say, because it's related to dam breaking phenomena, and the breach causes the failure of the dam, and after we have this flow traveling downwards in the river, if there is any river, because I'm thinking about the Kakova Dam, as you probably are aware, some weeks ago, a couple of 3 or 4 weeks ago in Ukraine, the madness of a person caused this tragic failure. And in Italy also we have some experience. I don't want to mention the history behind, but we are well aware of the tragedies occurring during the last decades. We use basically numerical simulation to reproduce this kind of phenomena. Basically, the SPH is a meshless technique, numerical technique. It is based on particle discretization, as you can see on the upper part of the picture here. And basically the properties of the red particle here is influenced by neighboring particles inside, let's say, a support domain. So it is a short-ranged kind of method, SPH. Here you can see better the situation. The support domain typically is a circular for two-dimensional simulation, or otherwise spherical one. And properties are derived using a weighting function, the Gaussian-like depicted in the picture here. We use basically the Wendland kernel function, which is a quintic polynomial written in the bottom of the slide. So as you can see, the function over a particle is simply the summation of properties over the neighboring one, the neighboring particles enclosed in the support domain. So, sorry, speaking about the governing equation written in this slide, basically the Navier-Stokes equation are discretized using the SPH technique. And we use some extra term in order to stabilize the simulation. Yes. First of all, the artificial viscosity term, which help dissipating high frequency wavelets present in the numerical simulation. And density diffusion term, which is present in the continuity equation. basically the meaning is related to stabilize the density field. We use a weakly compressible scheme, so basically in order to close the governing equation, an equation of state needs to be associated for problem closure, as you can see. Not much words on this slide, actually. Basically, we need to create the boundaries, because over the boundaries, that kernel function we have seen earlier is trunked, is cut. So in order to restore consistency, we need to apply special treatment. For instance, we use to modify the dynamic boundary conditions, which basically operates a mirror of boundary particles, the green colored here, into the fluid domain. Yeah, we use duals physics, basically an open source solver. And actually, my group is mainly involved in renewable energy applications, such as that one depicted in the movie, which is, let's say, a floatable platform with a theolic failure. So I'm coming to the case studied in this communication. Basically, we have this bridge cross section actually, and we have taken a previous paper for references. Basically, we have time history of water stages over this section WG1, WG2, and time history of pressure over the bridge. As you can see, P1, P2, P3, and P4 are the local probes over which the previous orders have measured time history of pressures. Let me answer it. 2 time, 1, 2. Okay, it should because it's yeah, this is the situation. This is the strength behind the method. You can simulate large deformation phenomenon. This is a problem for Eulerian kind of scheme. Well, it's way more complicated because you need to restore the regularity of the grid cells, no? Mesh regularization. Results, we are quite satisfied. Let's say it is better the comparison with experimental results for the water height in the first time of the simulation. Then we experience some kind of lag, as you can see. And yeah, I want to anticipate a potential question, maybe. Yeah, the reason it's probably due to the spatial particle resolution. We needed to push up a little more in order to understand if a finer size configuration helps with the comparison. Overall, we are quite satisfied in any case, because this is, I would say, so far the best comparison of a numerical approach compared with these experimental results. So we are quite satisfied. These are the comparison of pressures. The blue one is the SPH. compared with the experimental one. Yeah, of course, the total force experienced by the bridge, yeah, it is better again. The first one, the first part of the process, we get quite well the first spike of the force as the wave impacts the bridge. And then we have this, let's say, in the literature, you can find this kind of process, this kind of behavior represented by the steeple charge. It resembles a steeple charge in which a first maximum is present, the first peak, and then you get the second part of the charge on the right part. Yeah, coming to the conclusions, we got a quite satisfying comparison between our numerical results and the experimental ones. We got a good feedback in terms of pressures and water heights. And most importantly, probably, force predictions is quite good. Yeah, this is kind of 3D simulation of dam breaking phenomenon in 3D domain. Because yeah, this is just to tell you that my group is starting to simulating the interaction between moving waves, moving flows, and flexible structures. The color here is related to the deformation, the modulus of the deformation tensor. Thank you very much for your attention.
Thank you.